Okay, now let's continue on talking about hypothesis testing. So in the last video we talked about the various components comprising an hypothesis test. Now we're going to talk about the possible situations or scenarios that we will find ourselves in when we are drawing conclusions using hypothesis tests. So in thinking about the null hypothesis, HO or H naught, there are two possibilities. Either the null hypothesis is true or it's not true. And we're going to be dichotomizing our decision about the null hypothesis. We're going to conclude either that the null hypothesis is not true, or we will conclude that it's true. Now, we typically would, instead of saying concluding that the null hypothesis is true, we would typically state that as failing to reject the null hypothesis. And we'll talk about why we use that kind of terminology as we go along. But anyway, in terms of the true state, or the truth about the null hypothesis, there are two possibilities. In terms of our decision about the null hypothesis, there are two possibilities. And so when you combine those together, there are four possible scenarios that we'll find ourselves in. Okay, four possible cases. So the first case is that the true state of nature is that the null hypothesis is true, and that our conclusion based on the data is that the null hypothesis is true. So if the null hypothesis is true, and if the data lead us to conclude that the null hypothesis is true, then we have come to the correct conclusion. We've drawn a correct inference. Case 2. In case 2, the true state of nature is that the null hypothesis is true, but because of the data we get from the population, our conclusion is that the null hypothesis is false. So if the null hypothesis is in fact true, but we conclude based on the data that it's false, then obviously we have come to the incorrect conclusion. Now, statisticians, being the very creative people that we are, they came up with a very descriptive name for this kind of inferential error. It's called a type 1 error. Case 3 is the situation where the true state of nature is that the null hypothesis is false, but our conclusion based on the data is that the null hypothesis is true. So if the null hypothesis is in reality false, but we conclude that it's true based on the data, then again we've come to an incorrect conclusion. And this kind of inferential error, you guessed it, is called a type 2 error. And then case 4 is where the true state of nature is that the null hypothesis is false, and based on the data, we conclude that the null hypothesis is false. So if the null hypothesis is in reality false, and we conclude that it's false based on the data, then we have come to the correct conclusion. All right, so that's a good thing. We can summarize these four possibilities in a two-way table. And so in this table, this table represents the possible decision-making outcomes. All right, so here we have the columns representing the true state of the null hypothesis. Either the null hypothesis is true or the null hypothesis is false. Then we have the rows corresponding to our decision about the null hypothesis. So we either conclude that the null hypothesis is true or we conclude that it's false. And again, we typically, if we find ourselves in this situation right here, we would probably not make that statement as it's stated there. We would probably say something like, we fail to reject the null hypothesis. But anyway, so if the null hypothesis is in fact true, and we fail to reject the null hypothesis, in other words, we conclude that the null hypothesis is true, then we've come to the correct conclusion. We've made the right decision. If the null hypothesis is false, and we conclude that the null hypothesis is false, then again, we've drawn the correct inference. We've come to the right conclusion. On the other hand, if the null hypothesis is true, but we conclude based on the data that the null hypothesis is false, then that is a type 1 error. And then finally, if the null hypothesis is false, but we fail to reject the null hypothesis, then that is a type 2 error. Now, let me go back to the previous slide for a second. In a realistic situation, there's always the probability that we will commit either a type 1 error or a type 2 error, just as there's always the possibility that we could draw the correct conclusion. It depends on the data that we get. So there are positive probabilities associated with a type 1 error and a type 2 error in any given situation. What we want to do is we want to quantify the probability or the probabilities of those two types of errors. And so the first step in that direction is to define some notation associated with those probabilities. And so we're going to define the following probabilities and the associated notation. So we're going to let alpha represent a probability, and notice that it's a conditional probability because we've got that vertical bar there. But it's the conditional probability that we conclude that the null hypothesis is false, given that the null hypothesis is true. All right? So again, alpha is the conditional probability of concluding that the null hypothesis is false when in fact it's true and should not be rejected. On the other hand, beta is going to be the conditional probability that we conclude that the null hypothesis is true, or another way to say that, we fail to reject the null hypothesis, given that the null hypothesis is in fact false and should be rejected. So beta is the conditional probability of failing to reject the null hypothesis when in fact the null hypothesis is false and should be rejected. So these two pieces of notation here, alpha and beta, represent these conditional probabilities of the two types of errors. Another way to say this is that alpha is the probability of a type 1 error, beta is the probability of a type 2 error. Now, alpha also has another name, and it's called the significance level of the test. So when you see the term significance level, you know that that's talking about alpha, which is the probability of committing a type 1 error in an hypothesis test. Now, let's talk about the relationship between alpha and beta. The relationship between the probability of a type 1 error and the probability of a type 2 error. And it turns out that for fixed sample sizes, alpha and beta are inversely related. So if alpha decreases, then beta increases, and if beta decreases, then alpha increases. Now, another term and another piece of notation that we need, and another concept that we need, is the concept of power. And power is the probability of correctly rejecting the null hypothesis, in other words, concluding that it's false, when in fact it is false. So if the null hypothesis is false, we want to, we hope to get data that leads us to that conclusion. And so power is the probability of correctly rejecting the null hypothesis when in fact the null hypothesis is false and should be rejected. Now, in terms of probability, or in terms of notation, so power is this conditional probability of rejecting the null hypothesis given or when the null hypothesis is false. And by the complement rule, that is equal to 1 minus the probability of not rejecting the null hypothesis when the null hypothesis is false. Well, this conditional probability, if you go back to the previous slide, is just beta. So there's a nice relationship between power and beta. Power is equal to 1 minus beta, or we could rewrite that in a couple different ways. Beta is equal to 1 minus power, or power plus beta is 1. All right, so you can think about it in either of those three ways. And so going back to our two-way table, all right, where we've got a type 1 error down here, all right, so if the null hypothesis is true and we conclude that it's false, well, we've come to the wrong conclusion, that's a type 1 error. If the null hypothesis is false, but we fail to reject the null hypothesis, that is a type 2 error. And so now let's make a similar kind of table, but for the probabilities of these outcomes, using the notation that we've just defined. And so doing that, we have a table for the probabilities of the outcomes. And so alpha down here. This is the probability of a type 1 error. Beta is the probability of a type 2 error. Power is the conditional probability of rejecting the null hypothesis when in fact the null hypothesis is false and should be rejected. Remember that power is equal to 1 minus beta. And then this cell, which contains the probability of failing to reject the null hypothesis when in fact it's true, the probability associated with that is 1 minus alpha. So this column, we can think of it this way, this column here adds to 1, the probabilities in this column add to 1, and the probabilities in this column add to 1 as well. So that's kind of a nice way to remember that. Now, ideally, in a perfect situation, we would like the probabilities of the two types of errors to be zero. We would like there to be no possibility of committing a type 1 error or a type 2 error. In other words, we would like alpha to be 0, we would like beta to be 0, and we would like the power of the test to be 1. In other words, if the null hypothesis is false, we would like to always to be able to determine that and reject it when appropriate. But the reality is that in any given situation, there's always going to be a positive probability of a type 1 error. There's always going to be a positive probability of a type 2 error. And because of that, then power will always be less than 1. Well, if we can't have the ideal situation, we would at least like for both alpha and beta to be small, to be close to 0, and for power to be close to 1. But now remember, alpha and beta have this inverse relationship. If we decrease alpha, if we make alpha small, then what's going to happen is that beta is going to get bigger. And if we say, well, okay, let's make beta small, then alpha is going to have to get bigger. So, for a fixed sample size, we can't have our cake and eat it too. We can't have both alpha and beta being close to 0. In order to decrease both alpha and beta, we have to increase the sample size. And what that translates into is that we have to get more information from the population. And so that's how we can make both alpha and beta small. So again, there's always a positive probability for alpha. There's always a positive probability for beta. Power is always going to be less than 1 in a real situation, right? And so if we want both alpha and beta to be small and power to be bigger, then we're going to have to increase the amount of information we have from the population. And what that means is we've got to have a larger sample size. Now, when we talked about the overall idea about hypothesis testing, we said that we have these two competing statements, the null hypothesis and the alternative hypothesis. These are logical complements. And the way that we make a decision between the two is that we obtain information from the population of interest by selecting a sample. We study the sample, and we said that if the information contained in the sample is inconsistent enough with the null hypothesis, then we would reject the null hypothesis. Now, one way, and so the question we had at that point in time was, how do we measure this consistency or inconsistency with the null hypothesis? And we said we'd talk about that at some point, and here we are. So the p-value is one way of assessing the consistency between the null hypothesis and the observed data. So this measure is called the p-value. It's a measure computed from the data. It's a random variable itself. And we can think of it as a measure of the consistency between the null hypothesis and the observed data. So the p-value is a measure of how likely the observed results are if the conditions of the null hypothesis are true. Now, the precise definition of the p-value in words is that the p-value is the conditional probability of observing a value of the test statistic at least as extreme as that which has been observed if the null hypothesis were in fact true. Okay, let me say that again. It's the conditional probability of observing a value of the test statistic at least as extreme as that which has been observed in our data, computed under the conditions or under the assumption that the null hypothesis is true. Now, when we say at least as extreme, what that means is in the direction of the alternative hypothesis. And we'll see what that means a little bit later. But this is the precise definition of the p-value. And we could express it notationally, but in words, this is how we would define it. Now, just let me warn you, it is not, this is a common confusion. The p-value is not the probability that the null hypothesis is true. That itself is a conditional probability, but it's conditioning the other way, all right? So it's conditioning in the wrong way, or in a manner that's inconsistent. That's not wrong, but I mean, it's not consistent with how the p-value is defined. So don't confuse the p-value with this conditional probability right here. The p-value is defined in this way right there. The probability of observing a value of the test statistic at least as extreme as that which has been observed if the null hypothesis is in fact true. So again, the p-value is a measure of the consistency between the null hypothesis and the observed data. If the data are consistent with the null hypothesis, then the p-value will tend to be larger. On the other hand, if the data are inconsistent with the null hypothesis, then the p-value will tend to be small. And the more inconsistent the data are with the null hypothesis, the smaller the p-value will be. Right? And so when we talk about rejecting the null hypothesis, if the data are inconsistent enough with the null hypothesis, what that translates into is rejecting the null hypothesis if the p-value is small enough. And so how do we draw conclusions using the p-value? We reject the null hypothesis in favor of the alternative. In other words, we conclude that the null hypothesis is false and that the alternative is true if the p-value is less than or equal to alpha. And remember, alpha is the significance level for the test. So that's how we use p-values. We reject the null hypothesis in favor of the alternative if the p-value is less than or equal to the significance level of the test. Now, this is another way of deciding whether to reject the null hypothesis. Remember, the other way that we had was to take the value of the test statistic and evaluate it using the rejection region or rejection criteria. These two approaches, the test statistic and rejection region method and the p-value method, are completely 100% equivalent. All right, you'll draw the same conclusion regardless of which of those two you use. The benefit or the advantage of using p-values is that, and we'll go to the next slide where it says this, but the p-value allows different users or different consumers of a study, so people, for example, reading your research article, using the p-value allows different consumers of a study to reach different conclusions by using different significance levels. In fact, let me restate this. I think there's a better way to say this. And I think in the future I'm going to restate this a little bit differently. I think the way that I would restate this is that using the p-value allows different consumers of a study to reach their own conclusions by using their own significance level, by using a significance level that they are comfortable using. Because what we're going to find out, we really haven't talked about it yet, but what we're going to find out is that in setting up a hypothesis test, you as a researcher, or whoever the decision maker is, maybe the decision maker is a journal editor, maybe it's your boss or whatever, but somebody specifies the level of significance to use. Okay, so different people can use different significance levels, and by allowing or by utilizing the p-value in testing, that allows different consumers of a study to reach their own conclusions by using their own significance levels. Now, using a smaller significance level, using a smaller alpha, corresponds to requiring stronger evidence against the null hypothesis. Let me say that again. Using a smaller significance level is equivalent to requiring stronger evidence against the null hypothesis in order to reject it. On the other hand, using a larger significance level, a larger alpha, is equivalent to requiring less evidence against the null hypothesis in order to reject it. So that ends our basic overview of hypothesis testing. In the next lecture, in the next video, we're going to talk about estimation, and in particular point estimation and confidence interval estimation. So I'll see you in the next lecture.